Everyone, good morning. Welcome to today's webinar. We'll be talking about Leakage Testing 102. This is a follow-up webinar to our previously held webinar last month talking about Leakage Testing 101. In that webinar, we went over a lot of normal testing we do for line leakage testing, or leakage current testing as it's called. And we discussed the basics of the basic test, the earth leakage test. In this webinar, we'll be going over some additional tests that are required, especially applicable to a lot of medical industries or medical device manufacturing industry. And these standards, these additional tests that are required, they get a little bit more complex than what we talked about in the previous webinar. Before we get started, I'd like to introduce myself. I'm Bashan Patel. I'm one of the applications engineer here at Associated Research. We also have Tony Anthony Arroyo. He'll be a panelist for today. He could be answering any questions you may have in the middle of the webinar. So do use the question and answer utility to ask question, and Tony will be answering those questions live. And we have Brittany Socha. She's going to be handling the audio visual version of the webinar. Again, if you have any questions, do use the question and answer utility. One note is that if you have issues with audio coming from the webinar, please use the chat line to talk to Brittany, and then maybe we could have you resolve some issues. If you also like a copy of the webinar, please send a message to Brittany on the chat line, or you could email her. Her email address listed here, brittany.socha@airsafety.com. And we could provide you a copy of the webinar slides. If you want a copy of the video, the webinar is recorded, and we do archive our webinars, so please give us a few days and we'll have this webinar uploaded to our website under the archive webinar section. For today's webinar, Touch Current Testing 102, we're going to be talking about touch current. What is touch current? What constitutes a touch current? And what are the usage of, why do we run touch current testing? And why is it required by the standard? There's also other things like patient leakage. If you have any kind of patient parts that comes in direct contact with a patient, mostly in medical industry, or it could be any part of your product that comes in direct contact with either a patient or a human body, they categorize that as a patient leakage current. So we're going to be talking about how patient leakage current is measured. Patient auxiliary current is another form of patient leakage current. It measures between multiple points of patient leakage that you may have. And then we'll be talking about mains and applied part leakage. This is another scenario where worst condition that may happen, where someone comes in contact with a line voltage while they're connected to a medical equipment, and what kind of leakage current will flow to that person if the line voltage was coming in direct contact with the applied part. We'll be also talking about some kind of measuring device that's required by the standards. If the standard is specifying a measuring device, also known as an MD, this measuring device are specified in the standards to be some kind of equivalent, like a resistive and capacitive circuit that will closely match what a human body will look like to electricity. So we'll be talking about what measuring networks or measuring devices are called out for in the standards, and also some of the descriptions that are actually listed out in the standards. Now, when we say standards, the main standard for medical equipment manufacturers they have to follow is the 60601-1. Currently, they're on the 3rd edition, and the standard actually lists out plenty of tests that need to be performed. The above-mentioned tests, touch current, patient leakage, patient auxiliary, mains and applied part. Those are all encompassed in part of what they call leakage current testing. There's other requirement to keep the product safe electrically. So in the previous webinars, we also manufacture high-pot tests, ground-bound testers. These are all tests that are also required in addition to these touch current testing or leakage current testing. And medical industry is one of the one-off industry that do require these additional tests, because the applied parts are coming in direct contact with a human being. We'll be also looking at some of the examples and reference diagrams that we have straight out of standards, and then some videos that we have to show how an all-in-one box solution could provide your testing needs that are called out for these complex tests in the standards. All right, so let's define some of these leakage current test types. Okay, so touch current test. electric current that normally flows on top of a medical device or medical equipment could be classified as touch current. Anybody that comes in direct contact with the chassis of the medical equipment or a ground potential point of a medical equipment, they could be in direct contact with some kind of leakage current that flows on the chassis. Now, what makes this leakage current flow on top of the chassis? So you have your mains input coming in to power up the product. You want the mains input to do everything that the medical equipment is designed to do, but you also want to make sure that none of the current makes it to the chassis of the product. So what manufacturers do is put insulation around the live conductors or the live part of the circuit to isolate that live circuit from any other conductive part of the equipment. Now, in the standards, they call out for at least 2 means of protection, MOP. So means of protections are barriers that you set in your medical equipment that don't allow the leakage current or normal leakage current to flow to either the places that you don't want to flow to. Example, the chassis of the product or the ground stud of the product. Now, this could be also classified as enclosure leakage. So if enclosure leakage current that may be called out in the standard is similar to a touch current point, which is not grounded. So if your medical product has a metal plate or some kind of metal conductive section, it could potentially get energized in a sense that if the insulation barrier that we talked about does not hold up, or some manufacturing defect has gaping holes in your insulation or pinch insulation or pinhole insulation, all this stray leakage will leak towards either the chassis or this metal non-conductive part. So an enclosure leakage kind of measures anything that a person could come in contact with and maybe significant in a path of getting electrically shocked. When we're talking about patient leakage current, the second one down, the current flowing from patient connection. So what are patient connection? Now, when you're working with medical equipment, there's medical equipment like a bed that has that you may think is not a patient connection. There's no connection on a medical bed. Like a hospital bed has no connection points to a patient. But if a patient is going to lie on the patient is going to be on the medical bed itself, you do have a point of contact to the patient. So if your bed has any kind of electric motors or the thing that pushes it up and down, you have electrical signals coming into the bed. Now you want to make sure that those electrical signals don't make it onto the patient itself. So you want to protect the patient from coming in contact with any kind of live voltages that the bed may be plugged into. So patient leakage could be as simple as anything that comes in contact with the patient while they're under the inside a medical facility, or it could be some outpatient facility, or it could be a doctor's office. Think about oxygen sensors or electrodes for EKGs. EKGs are a good example of how it conducts measured signals on your body, but it also has a part of inside the medical equipment, there's a part that sends signals towards the electrodes to make sure it's sensing it properly. Now you want to make sure none of the mains voltage make it out to this applied part. So how do we do that? We make sure that the patient leakage current is below the specifications that are set up with this standard. Any current flowing from this patient leakage connection to earth is considered patient leakage. So if I'm connected to all these EKGs and then the medical equipment is measuring my heartbeats or heart rhythm, and any leakage current that's felt by me is considered patient leakage. Now, a lot of medical equipment have more than one patient connection, so there are additional tests that are required. They're called patient auxiliary, which is measuring between two electrodes, or two patient parts. When you have more than one applied part that comes in contact with a human being, and if the functionalities are different, so if one is measuring something for heart rhythm and the other one's measuring the oxygen levels, they have two different functionality. Now you have to measure the leakage current that may appear between the two applied part. Now, when it comes to patient auxiliary current, you also want to make sure that the voltage, you don't have any kind of inherent voltage appear on these 2 points while the patient is connected to the applied part. And the fourth one is mains on applied part testing, or mains on applied part leakage current testing. which ensures that if you have a patient that's connected to your product with all these applied part connected to them, what would happen if a line voltage somehow makes it onto those applied part? Is your medical equipment or medical device going to cause any sort of leakage current to flow through this human or the human being, because now the line voltage made it onto the applied part? It's possible that line voltage coming onto a human being while they're in the hospital bed may or may not kill them because they're sitting on a hospital bed which is isolated from ground. But it doesn't mean that the medical equipment that they're connected to could cause additional damage to that human being. So again, mains on applied part test is taken into a worst case scenario where a human being or comes in direct contact with a line voltage, and hence it also comes when line voltages are applied to your product. Products applied part section. So we talked about leakage current types. Now let's talk about the patient leads. So main aspect of having leakage current testing done is to have, if you have any kind of patient leads. Patient leads are important to classify in two different sections. There's a B-type applied part that comes in contact with a patient. So my example of a hospital bed is a B-type applied part. Usually there's a basic level of protection provided for shock hazard, and this basic level of protection is usually a grounded surface. So if, instance, a metal part of the bed is grounded through the line's input of the mains mains conductors, you're officially grounding that product. Once you're grounding a product, you're providing a basic level of protection from any kind of live voltage by grounding the product. You could also have any kind of metal enclosure part or metal chassis product that is grounded, and since it has an applied part that's also ground reference, this could be considered a part type B applied part, meaning that it only has a ground reference point as grounding as a mains of protection. When you go over to F type applied part, what are F type applied parts? Applied part in which patient connects are isolated from other parts of the medical equipment. So this means that when I have my medical equipment or medical device that has all these live voltages coming into the product, I have these applied parts that have nothing to do with the live parts of the circuit. So I have enough isolation barriers between my live circuit and these applied parts that I'm going to let the applied parts do the work that it needs to be doing to kind of collect signals or collect any kind of waveforms or things like that, but they have no referencing back to the main circuits of the product. So having those protection put in place, I still have to verify that there's no stray leakage making its way through the protection I just put in. So when I have two means of protection between my live circuit to my applied part, I'm running a patient leakage test to make sure that during when my product is powered up, it doesn't leak any leakage towards the applied part. So my example of EKG leads, for instance, so if I have an EKG lead connected to me, I want to make sure nothing that comes out from the wall is ever coming towards the EKG leads, because what could come out of that is that if the insulation barriers that I've put in and not in place or not properly in place, I could be at a potentially shock hazard conditions where anybody connected to those EKG leads could be shocked. Now, F-type products are floating reference, meaning they have no reference to the line inputs, line, neutral, and ground. So when they're floating, they provide automatically they provide some kind of layer of protection since they're already floating. So now standards is asking that once you have a floating applied part, we're going to stress this applied part even more to make sure it's a properly rated floating applied part. Now, the F-type applied parts are also split into two different sections. There's a section type BF. Again, this is a type of applied part that provides a higher degree of protection compared to a type B. So initially we talked about how B is just referencing to ground to kind of provide one layer of protection. Type BF is floating, plus it's providing an extra layer of protection to ground. And then type CF. So CF type products are the highest degree of protection that you could provide for electrical shock. Now, these type of parts are usually that come in direct contact with either your tissues of for a human being, or blood vessels, or any kind of muscles and inside of your body where cardiac system is in direct contact with electrical signal. Now, microamps leakage in CF type product is very dangerous because now you have a direct contact to any kind of electrical signals in your body. Other types of product that don't puncture your skin, since skin is providing the biggest level of insulation, you could get away with not having the amount of current that's needed. But when you get to a CF type, a cardiovascular direct connection to cardiovascular system of your body, you need additional protection, additional layer of insulation that protects any kind of leakage current from your product leaking onto those ports. Again, think about a surgery equipment, right? So you have a drill, the doctor's drilling on you. Now that drill gets the power from the line's input, like they're plugging into the hospital's main inputs. Now the medical equipment has to make sure none of the current from the line makes it onto the drill, referencing to either the patient or ground, because if the leakage current happens when they're doing the surgery, that could have adverse effect and a potential electrical shock hazard at that point. The biggest important factor that determines how a leakage current test is performed is that you need a measuring device. Leakage current is measured through a human body impedance network. So a medical standard like a 60601-1 will specify what kind of medical device or measuring device should be designed to kind of simulate a human body. There are different types of measuring device that's possible for different standards, but when it comes to majority of these standards only ask for some kind of capacitor and resistor network to make sure they're covering a broad range of conditions that may happen during a hospital visit or during the condition for line power, basically. So when you have a hospital that doesn't get any clean power, are you simulating the proper frequency range where a frequency might be at 50 hertz, may have also other aspect of the frequency in the line power. So if you have not a dirty power coming out of the wall socket at a hospital, you plug your medical device in. Now, are you able to simulate this properly where a human body coming in contact is able to kind of measure the correct leakage current? So again, different types of standards call out for different kind of measuring device called MD, and we'll later see how these MDs are attached to your the device under test to kind of measure different points that we mentioned earlier, and see how it measures the resulting leakage current flow. Now the MD is also again meant to be like a substitute for what a human body impedance network will look like to electricity. And then the standards calls out for single fault condition. They're looking for these fault conditions. So another important aspect is what kind of fault can you expect when you are at when this product could be plugged in. Did the electrician wire the ground in properly? Is it ground missing? Did the electrician wire line neutral in properly? Is it now neutral one line versus line neutral? So all these single fault conditions that may happen are kind of accounted for when the standard calls out for single fault and a normal condition leakage current testing. Another example could be, do you want to make sure, what if somebody breaks off the ground pin? You sold all your medical equipment to a hospital and somebody that didn't know any better breaks off the ground pin of the product. Now, even though the outlet has ground, you just defeated a safety mechanism that was provided by your design engineers. Somebody breaks off the ground pin and they plug it into the wall. Do you want to be dependent on somebody that creates this kind of fixes for some situation they may have, that your product starts leaking more leakage current now? So if you're running these single fault condition where ground is open, you're able to kind of tell if what would happen to your device, what kind of leakage current you would have coming out of those applied parts or enclosure points, to make sure that they're not leaking above the required limits that are set up by the standards. As I mentioned earlier, there's different types of measuring devices. Our instruments are capable of up to 7 measuring devices, and then we also have one where you could create your own measuring device if it's not listed in our instruments. Take a look at the left side here. We have a, sorry, one second. Just having a little difficulty with this here. So we have the medical device here. So this asks to have a 1K ohm resistor. Normally that's what they ask for. And then there's these frequency responses where they're checking for more than just the 60 or 50 hertz that may come through. So if there's any other, something else is leaking in your product, let's say you have for example, a defibrillator, and if you're connected to a defibrillator, it might be sending some current in different frequencies. So up to 1,000 hertz may be harmful to a human being. The resistive network, the capacitive network here is kind of to ensure that you're measuring the full range of the frequency or the voltage that may be seen on the product. You also have IT equipment. In IT equipment, there's a requirement to have earth leakage. In earth leakage, you may need to be you may need the measuring device that's listed out, and we get this straight from the standards, and standard requires this kind of complex RC circuit to kind of measure the leakage current that's flowing through a human being. And then there's also electric spa category UL 1563. That's a standard 500 ohm in parallel with a 0.45 microfarad capacitor. Again, these are measuring devices. These are set in stone. They do change once in a while, but majority of the time they're referencing back to one particular standard. And for us, since we have 60990-1 is the main circuit where all these other variants of the circuits come from, so for medical devices, it's the 60601 figure listed right here. So how do we do this? So we want to make sure that when we say a measuring device, the measuring device is internal to our instrument. If you take a look right here is our device, the 8206 or 8200 series Omnia 2 instrument. You have a medical device here that's going to be plugged into an outlet that comes out of our medical Omnia tester. It's going to provide line, neutral, and ground connection points. So you have line, neutral, and ground connection points. We're going to actually power up this device. So one of the important things about doing a leakage current test is that the device has to be powered up to the full potential. So the temperature, the normal operating temperature, the normal operating screens, and normal operating procedures, the device has to be fully powered on. Once the device is fully powered on, now you can start making measurements. And in order to make measurements, you have to let the tester know where those 2 points are. So when we look later into our the medical standards figures, I'll point out how these conditions come into play, where the tester itself needs to know where this enclosure point is. The tester needs to know where this applied part is. You may have more than one applied part, so the tester needs to know where this other secondary applied part is. And when we're doing a patient auxiliary test, you need to know what's my leakage from this one applied part to this second applied part. So I have to be able to tell my tester where these 2 points are. And we do that using what we call probe high connection point and probe low connection point. This is no different than taking a DMM and measuring a voltage between 2 points in a circuit or 2 points on your device. But a DMM is not going to tell you, does not have the measuring device built in. So a few things I mentioned earlier about needing a measuring device to kind of accurately simulate what a human body current will look like. You do have to turn the device on to the normal operating conditions. So if you have a heater, for instance, that heats up for that somebody goes into the your medical device is a heater and it needs to heat up to this level, then you want to run your medical device for the first 60 seconds to get it up to a normal operating temperature and normal operating conditions. So the earlier image was showing you how the connections are made. This is more a simplified version of what's going on with the connection. If you look at the left side here, the left side is where our Omnia 2 or one of our 620L measuring leakage current measuring devices our instruments are. In here, we're doing some of the switching that's required, or some of the schematics that are required by the standard. You have your device under test, your medical device, that's going to be plugging into one of the adapter boxes. Normally, we'll provide line neutral through either the internal power source of our Omnia, or if the currents are too high, additional extra line input may be needed. But what we're doing here is providing line to your DUT or device under test, and then neutral for DUT for it to power on. And then we have this thing called a measuring device, an MD, that's internal to of our instrument that's going to make all your measurement. So initially you have switches that are called out by the standard in the diagrams. S1 is open neutral. So if I have a switch where I could open the neutral to see what kind of leakage current could be seen on my device, the standard will ask you to open this switch S1. At that point, the device may or may not turn on, but it's still receiving line voltage reference to ground or reference to a reference point. So you may think, oh, the device is not on, it's not going to leak any current, but it's still possible that leakage is still presented on the chassis or an enclosure point on an applied part. The standard also asks to do what they call S2 or polarity switch. This is again simulating what if somebody wires the wall outlet reverse. What if somebody has it line neutral and now neutral line, and now you're plugging in your product. Does your product leak more current because the wall outlet now has neutral line versus line neutral? And the third condition is open ground. So when you have an open ground condition, you would expect the most leakage current from your product. Why? Going back to our type B product, if your type B product has ground as a one layer of protection, even if I come and touch the device and the test, the ground is taking care of most of the current going to ground. So you may see zero leakage current through this network here because the ground is still acting as the protective network. Now in an event that the ground is opened up either by miswiring or somebody breaking it off, or in your manufacturing process somebody forgets to connect the proper ground, the DUT has a ground pin but somebody didn't put the screw in there. So if that case happens, then you would see an extra leakage show up through the measuring device. So let's take a look at the conditions that we just talked about. We have a normal condition, it's NFC, NC, sorry, normal condition. In a normal condition, you have line voltage going to your DUT, basically it's going this way and it's coming back, and the device is powered on. There will be nominal leakage, but the leakage is taking the path through the S3 switch. Now, since the S3 switch is closed, means the ground is there. S1 is the normal polarity, meaning it's line neutral, and S1 is also closed, meaning the neutral is closed. So when neutral is closed, reverse polarities are the normal polarity, and the ground is there. This is what you expect your product to be. You want your product to operate in a normal condition. So you don't have an open ground. No one has miswired the line neutral, and then you don't have an open neutral. So when you plug this device in, the ground is taking the current that's flowing is being taken care of the ground circuit. So this MD is never going to see any leakage current because the ground is taking care of the current. Then we have a condition called open neutral. When you have an open neutral condition, again, your line voltage is going all the way to your DUT. It may or may not create leakage current, but again, when you have a ground closed, the leakage current still bypasses your MD measuring device, and it's not being seen by the MD. Reverse polarity. Now let's say you have a line that's connected to the neutral and then a neutral that's connected to the line of your DUT. Again, your device may power on because the engineers designed it to be powered on for neutral line or line neutral condition. But then again, does it leak extra current? That's the kind of things we want to measure. Like what happens when the reverse polarity condition happens at the line mains input. And then the condition for open ground. So we talked about S1, S2. Now S3, that's the biggest thing, right? Once you break the ground pin on your product, you're going to create leakage that flows to the measuring device. So you have a measuring device here, a measuring device in line, touching the chassis point or a ground equipotential point. It could be a metal conductive point on your product. Line of the product is powering up the DUT. Neutral is going back to power up the DUT. So this is where the current flows for normal product. But there's another leakage current that's happening, right? So now you have line going into your DUT. Now remember what I said, there's live circuit in your DUT that's isolated from ground and applied parts or any kind of patient connection points. What if that insulation wasn't good enough? Now if somebody breaks off that ground, now you're going to start seeing a leakage that comes to the chassis of the product, which is then picked up by the MD, referencing back to the neutral side. So the flow that happens from line to ground is called earth leakage, so ground to line. And then if the flow is happening from line to an applied part, so let's say you had a patient part here, any leakage that's fell through that way coming back to the MD is called your patient leakage current. So I like to stop here for a few seconds and just to make sure that everyone's paying attention. We have a poll question here where it asks you, it'll give you a few different conditions, and the question is, which of the following will create the maximum amount of leakage current through the measuring device? So I'll have Brittany put up that poll question and give you a few seconds to answer the question.
All right, Bashan, we had 11% say ground closed, neutral closed, and reverse on. 78% said ground open, neutral closed, and reverse off. And 11% said ground closed, neutral open, and reverse on.
Okay, thanks very much, Brittany. So again, this is something that we've seen when we go to our site visit, when we are doing our consulting at customer sites, that there's these conditions that people have written down for their procedures, but they don't account for all types of conditions that may happen. So the standard is asking you to do a single fault condition. Since there's 3 switches that could be either on or off, this potentially creates 8 different conditions that could happen, either a single fault or double fault. The correct answer is the 78% that answer open ground. You're taking it into account where a ground is opened up. It causes extra leakage for your product because the one layer of protection that you have in place, somehow it got defeated by either somebody breaking off the ground plane, connections not being made properly, or the electrician didn't wire the ground properly. So in an event like that, do you really want your medical equipment that's already connected to the patient shock that patient? You don't. So basically what you have to do is you have to consider this situation where ground could be open, and you want to make sure that leakage current, it may be leakage current there, but it should be below a particular value listed out in the standard. And normally this is listed out as 5 milliamps to 10 milliamps of leakage current, which we'll see later on when we pull up the tables for leakage current testing. So I mentioned the standard 60601, but here's a kind of reference guide to where these requirements come from. So if you look at clause 8.7, leakage current and patient auxiliary current testing, it asks you to run some single fault condition and a normal condition to kind of simulate these different switching that may happen inside or in live condition where a ground is broken off or neutral is opened up or reverse, maybe polarity may be reversed. One of the requirements that I haven't mentioned is that they request you do a high line test, meaning your voltage should be at 110% of the normal operating voltage that you expect this device. So if you design your products to be operating between 100 volts to 240 volts, now you want to take the maximum amount of voltage that your product is meant to be ran at, 240, and then you want to add 10% more voltage to that. So the reason they do this is to account for any kind of variation you may have, an additional line power that's not at 260, or it's not at 240, but now it's at 260. What happens to your device? Do you want your device to shock somebody because they plugged into the wall where it's 260? Your device may still operate, and at 260 is leaking a lot more current. So the standard is asking you to run a higher voltage than normally what your product would see, and this is usually 10% higher than the maximum voltage that is meant to be operated at. For a 240 volt product, generally 264 is the standard, so you want to run your test at 264 volts. And then you also want to consider the frequency. So if the highest rated frequency is 60 hertz, you might want to check and make sure that If your product is this, even though it's going to be sold in Europe and they're only going to be running at 50 hertz, you want to run the test at 60 hertz because a higher frequency may cause it to have additional leakage current that you're not aware of. Now, what are the passing criteria? So we talked about the requirement. You got to power up a device, your device you're testing. You have to make the connections to make sure the probes are connected properly, and then you'll make sure the voltage is at the right voltage, and then you have these simulating conditions. So these are all the requirements to kind of get this test set up. But what is the passing condition? So let's look at earth leakage testing. This earth leakage is nothing more than I have a medical device, somebody broke off the ground pin, and a patient comes up and touches the medical device. Now the path that the current is going to take is through the patient. So that's known as the earth leakage. Is usually required in a normal condition to be around 5 milliamps. So less than 5 milliamp is what the requirements are. If there is a fault condition, so if there is an open ground that may happen on your product, or reverse polarity may happen, this requirement goes up to 10 milliamps. So usually 10,000 microamps or 5,000 microamps are the same numbers as 5 milliamps and 10 milliamps. When it comes to touch current testing, look at the number is a lot less. Now it's up to 100 microamps of current that's allowable. So you went from 5,000 microamps to now 100 microamps in a normal condition and 500 microamps in a single fault condition. So again, if you had an applied part, if you had these EKG leads that are going to be connected to a patient, you should expect no more than 100 microamps of leakage current to those applied part. Because what could happen is that the patient is connected to 50, or no, not 50, but 5 or 6 applied part at one time, and all those currents are going to add up. So you want to keep the current that's flowing from your applied part as low as possible. And the single fault condition here, it points out that you go up to 500 microamps. Again, that's 0.5 milliamps. But again, these are for your touch current points. They're not effectively grounded by earth or has that floating. Remember the F-type applied part. Anything that's F-type applied part should be tested to make sure the leakage current on those points is not, at least is less than 100 microamps for normal condition, and 500 microamps for single fault condition. And then patient leakage, it tells you to refer to a table. Now the table has both AC and DC equivalent of leakage current, depending on what type of products you have, depending on what that applied part is doing, you may or may not have different leakage current requirements. So we'll go over that table in a few slides, but just wanted to point out where to look for these requirements in your standards. Now, everybody that manufactures medical equipment should have at least the standards a copy of the standards with them, because there's no other way to get this information other than getting directly out of the standards. Now, where does it talk about the actual leakage current measurements? So if you take a look at clause 8.7.4, it talks about earth leakage current. It uses figure 13. So we're going to go over this is where figure 13, well, actually we're going to go over figure 14, but figure 13 describes where to make the measurements for your earth leakage. Touch current, also known as an enclosure leakage, figure 14 it should be used in section 8.7.46. Patient leakage general. So this is about all those applied parts that we talked about. That section splits into multiple different sections. You could have patient leads to earth, mains on applied part, mains on signal IO. So think about your product having like a Ethernet card. That's a signal input output section of your product. What happens if there's like voltage on that? What if an IT guy in his IT room applies line voltage to the Ethernet cable? So line voltage made it into your signal input port. Now, how does that be detrimental to the patient that's connected to your product on the other side? Does that line voltage create additional leakage current to the patient that's connected? So these are kind of tests that they want you to run to make sure these unseen circumstances that may happen doesn't cause additional leakage current to show up on the patient leads or any kind of touch points. And then patient auxiliary basically is patient leads to patient lead. So if you had one medical equipment that has 4 or 5 different parts that connect to a human being, and they're doing all doing 4 or 5 different functions, they're individually coming out of the different circuits on your medical equipment. So now what happens if one of them is malfunctioning and other one is you may not see, you have to kind of account for this where the leakage current may be present between the 2 points. So if the current could be flowing out of one lead, going back into the other lead, and this is what we call patient auxiliary leakage current. And this will all clear up when we look at some of the images that are actually figures that are pointed out in the standards. So let's take a look at, okay, so we have the table 3 that Abo mentioned that tells you refer to a table 3 in the standards. Table 3, if you take a look here, that we have the patient auxiliary current, patient leakage current, and the total leakage current. So if you have patient leakage current to earth ground, these are your limits for AC current. 100 for type B applied part, 100 microamps. You have some they're calling out for 50 microamps, the CF type. Again, the CF types are more stringent. They provide a additional layer of protection. That's why the leakage current now is into the 10 microohms, 10 microamps range, because this is going to make direct contact with the cardiovascular system of your body, direct contact with the electrical signals in your body, and muscles and blood vessels and tissues. They conduct electricity pretty good, So at that point, your leakage current has to be in the 50 microamp range. So when you're buying testers, you got to be able to make sure the testers are able to measure sufficiently down into 50 microamps with good accuracy. Again, refer to this chart or table and to get your high limits for your currents depending on what type of products you have and what kind of applied part you have. And also tells you where to look for these. So the figures that are mentioned here, figure 19, figure 15, 17, and so on. Moving on, taking a look at another table here. Now we have a similar chart. Now this is for earth leakage, patient leakage current, and mentioning the different types of conditions that you may have: single condition, normal condition, single fault condition, and also list out earth leakage for equipment, for any equipment that's connected to earth, something that could be floating, and the different ranges that it requires you to have. So let me go back a second. So when we talked about figure 14, okay, so this is the touch current section of what the standard is calling out for. So if you see in your documents that it says, oh, refer to figure 14, or we want to perform this test according to figure 14. So initially this image may look like there's a lot of stuff going on here, but to simplify it, let's take a look at what this is. You have mains input, the T1 transformer. This is what basically powers up your device under test, or the medical device that you're testing. So I have this EKG monitor. I need to provide some line voltage to it. This is where T1 comes in. It needs to be an isolated power supply to make the testing safe and measurement be more accurate. So that's why you have mains input coming in, a T1 transformer providing an isolated power. You have a line voltage going to your product and a neutral going to your product. P1 points are your points where the product is being plugged into the wall. So you have a line and neutral, and you could either have a protective earth, the PE that's listed out here, and some equipment may also have the functional earths. But let's just talk about the protective earth for a second. So you have line, neutral, that's going to power up this medical device, and then you have this protective earth that's going to ground any kind of metal and points that somebody could touch. So again, that's the first level of protection that's being provided. You have your switch S1. Again, an S1 switch is the open neutral switch that's open to simulate an open condition. If cuts off the wire to neutral, or the neutral wire is disconnected in your product is still receiving line voltage. It may not turn on. Somebody may think it's off and goes to touch it and may get shocked. So again, S1 is the open neutral. S5 is your reverse polarity switch, and then you have a S7 here for protective earth signal. So again, 3 switches, two different states could create up to 8 different combinations. The most important fact about what makes it a touch current test is where the MD lies. So if you had to imagine what an MD is, think about MD having a right hand and a left hand. I'm going to simulate a measuring device, a human being that's here, has a right hand that's going to come in contact with the chassis of your medical equipment, and the other side is going to reference to either ground or the low side of the transformer. Now I'm creating a path. So normal path to power up this product is that it's going to go to line, come back to neutral, and it's going to power up the device. All the lights are going to light up. that's in place to kind of handle the touch current. Another way of having touch current could be that the MD, the measuring device, comes between two different points. So you could have a non-earth metal contact point here. You could have a non-earth metal point here. And if somebody comes in contact with those 2 points, what is the resulting leakage current through your measuring device? And that's what we're measuring. We're actually measuring the voltage that's between these 2 points, and that voltage through a 1 k ohm resistor and some other capacitors will create our meters to go off here, and the meters will actually read maybe around 10, 15, 20, 30 microamps with this, which is below the limits that are required. Let me see, give a second. Again, touch current, another way of having just one applied part. So the last figure, figure 14, talks about the outer shell of your product being earth grounded, and you want to check the touch current to that point. What if you want to check to the touch current to your applied part? Again, number 4 here kind of indicates where your applied parts are. So these are applied parts are isolated from this circuit back here, and they should not see any line voltage ever, because these are going to be applied to a patient. You don't want to shock the patient. So you have all this barrier in the middle. Now, any kind of stray leakage that goes out to the applied part, we want to be able to measure that. So what we do is we connect our measuring device, again, right hand of the MD, could be connected to an applied part. You could also short these together if they're doing the same function. So you could short your applied parts together to measure a cumulative leakage, and you have to reference back to the chart to see how much total leakage current is allowed. But again, you're shorting out your applied part, MD is coming in contact with it, you're powering up your device normally, it's gonna run, do its things, but it'll also leak some amount of leakage current to the applied part, and that's what we're measuring back to the transformer low side. So MD is in the middle. Again, same rule applies. If the S7 switch, protective earth, was closed, you will see almost no leakage. When you open the S7 switch, there's no longer ground on this device. Now, you may or may not see additional leakage there. So again, figure 15 talks about patient leakage as concerning where patient leads are connected to a patient and how that leaks back to the source. I do have a video I want to go over to demonstrate how this happens with our instruments that we sell and connecting a medical device to it. So let me pull up that video really quick. All right, so let's just go over this really quick. We have the diagram that I showed earlier that had line connection, neutral connection, and a ground connection. So imagine this being your wall outlet, line, neutral, and ground. This is where the device is going to get the power from. So some of our instruments do have a built-in internal power supply that provides line, neutral, and ground. And you have your probing condition that may or may not be required for your leakage current testing. What you're going to see next is that goes to an adapter box. So you have your, again, line, neutral, and ground where a medical device is plugged in. And since this medical device did not have any metal points that we could touch, it's all plastic. So this medical equipment was all plastic, doesn't have any metal parts that could be energized, but the standard still wants you to check for leakage current on this kind of product. And what they ask you to do is either take an aluminum foil that's a size of a human hand to kind of replicate some kind of leakage current that may flow through the plastic material that's here. So that's why you have a connection that's being made. This connection goes to what we call the probe high lead of our product or our instrument, and it's connected to a conductive aluminum foil, which covers majority of the area that may leak the current. Now, the standards also ask that you put the aluminum foil in the highest leakage point that your device may experience. So if you have a point where you know it leaks 60 microamps, and some points they leak 10 microamps, you always want to perform your test at the 60 microamp points. Again, this is the medical device being connected. So this is our 8257 Omnia instrument. This does a leakage current testing along with high pot test, ground bond test, IR test if you need it to do, and then leakage current testing. Plus, it also does a run test. But since it has an internal power source, we want to be able to make sure that internal power source provides the power to device to turn on. Going back here just to make sure, we're checking to make sure the internal power source is turned on. Once we see that, we want to go into setting up the actual test files to make sure our probe conditions are correct according to what the standards or the figure we're looking at. So these are some of the parameters that they're needed for your product or product to be tested properly. Leak high, leak low limits, again, they come directly from the tables that was referenced. You could look at the standards and figure out what your leakage high may be. You could have anywhere from, I believe it was 10 microns was one of the lowest that you could have for type CF product, all the way up to 10,000 microns. So these limits for leakage high, leakage low come directly out of the standards. Voltage high, voltage low, again, this is where if the standard is asking you to run a test for more than 110% of the voltage, you want to make sure you get to that voltage. So if your testing is required to be ran at 264 volts, you want to ensure that the voltage is around 260 versus volt low is 260, and then volt high could be 270. So you want to make sure you do the proper test. The product is being tested at proper voltages. Now the dwell time usually is called out in the standards. It will say run the test for 5 seconds, 1 second. This could be also internal standard. You could have a dwell time that you may need additional dwell time. Delay time is really important. When it comes to delay time, you want the unit to power up properly. So once it receives the power, there are some devices that may need additional time to power up properly. So if you have a device that needs 60 seconds to power up, to go through the boot cycle, get it to a proper operating condition, delay time is where you will put this timer in, where we're not making a measurement on your product until the 60 seconds are up. So we allow the first 60 seconds for you to turn on the switch, for you to kind of get the product up and running to the proper operating conditions for us to be able to measure properly. The conditions that are called out for the switches, right? So we have the conditions for, let's talk about the measuring device, sorry. So measuring device that we have called out for in the standards, you're able to easily pick which measuring device is selected. So in here, we're gonna select the 60601 standard. Again, the graphic shows you which measuring device you're selecting, and the measurement is done between point A and B. Any kind of leakage flowing through that resistor is going to be measured by our measuring device internal to the device, internal to the instrument. Next, we're going to take a look at the conditions for probing conditions. So we talked about ground to line, where when you have ground which is open, you want to be able to measure the current flowing to the enclosure, or sorry, on the chassis of the product. That's known as the protective conductor current, also known as the earth leakage test. And for this test, we're going to be using the probe high to line because we want to do the touch current test. Again, if you take a look at what the switching is doing, the MD is your measuring device, which has 2 arms. Imagine right arm touching a point. So I'm going to tell the instrument here that you have to measure at probe high and measure any current that's going to flow through it. So once we look at the product, I'll show you what those probing points are. And want to make sure some of the other settings, if you had AC, DC. For internal source, we do want to set our internal source properly to output voltage. So here's how we set our internal source to output proper voltage. Just going to let this video run. And when we're running the first test, I'll show you what indicates that this is a normal condition. So there's only 2 tests in here. The first test is ran as a normal condition. So you could see that neutral, reverse, and ground, there's no LEDs indicating that there's any fault. And the resulting leakage current, since the ground is closed, is leaking 0.1 microamps. So this is your probe high to line connection. The probe is connected to that aluminum foil that's wrapping the medical device, and there's hardly any leakage when the ground is closed. Now, the second test, so this is going to run for and then again, you have to have your device turned on. So once the device is turned on, again, the leakage is still nominal. This indicates that ground is opened up. So the LED that came up that says open ground. So when the ground opened, now you're leaking 25 microamps of current onto that metal foil. Again, the metal foil is picking up 25 milliamps of leakage current for the touching points, which is the it could be the metal point on your product, or it could be through the plastic that comes through. And just going to show you another point. So you have your the aluminum foil takes care of your touch point. Another touch point is also your applied part. So applied part is going to come in direct contact with the patient. So you want to be also run the same test with an applied part. Again, this is a manual process, but we have other ways to kind of do a fully automated station. We call the switching matrices, which I'll get to in a few seconds. Again, we're powering on the medical device, hardly any leakage for a normal condition. And then we have an open ground condition that's leaking almost close to nothing, again, 0.6 microamp. Why? Because that applied part is so isolated from ground. Sorry, that applied part is so isolated from the line neutral coming into the product. There's only straight close to zero leakage coming out at the applied part, because there's a lot of barriers between those live circuit versus this applied part. And I know we're kind of running short on time, but let me just go through some of these additional slides. We may go over about 5 minutes. So this is where we talked about patient auxiliary, right? So you have two applied parts doing two different functionality. Take a look at where the MD falls in. Your MD is now between probe high. Sorry, their MD is right between applied part 1 and applied part 2. So I'm measuring now if the two EKG leads that are connected to me, is one EKG lead going to cause current to flow between those 2 points to the other EKG lead. If I don't run these tests, I would never know what kind of leakage current a human may feel when they're coming in contact with the product you're designing. So again, you're going to power up your product normally. You have all your switches here, open ground, closed ground, those are all fault condition, but your measuring device is now between an applied part. So this is what we call a patient auxiliary leak current test, and this is measured between two applied parts. Let me pull up that video really quick. Let me see. All right, so again, same setup as before. You have line, neutral, and ground, but now the main important factor is I have probe high and probe low. I have to be able to tell my instrument where these 2 points are. So unless I tell it where these 2 points are, my instrument would never know. I have to tell it where this point is and where this point is. So I'm going to use the probe high and probe low to kind of tell it where the MD needs to fall in. So we go back to this video here. I have these 2 points coming out of the instrument, and once I connect those to a proper points, the test will be ran between those 2 points. So here you see one of the probe point is connected to signal input points, which obviously somebody could come in contact with. And the second point that is connected is going to be connected to the applied part. So this is an applied part that's connected. So now you're measuring between this red lead and the other red lead. If somebody touches those 2 points, is there any leakage current coming through the product? So again, we'll run through this test to see what kind of leakage current is seen between those 2 red leads. We're going to run again normal condition test, but we had to change our probe condition, right? So we initially had probe high to line. Now we're going to change that condition to probe high to probe low. So I'm putting my MD between those 2 points, and I'm going to run the same test we ran before. First, we're going to change probe conditions for both. Okay, so here's how we set those probing conditions properly. And once the probes are set properly, now you're performing the patient auxiliary. So you went from performing touch current test to patient auxiliary test by just switching out the probes. And now you could see here where it says probes are probe high and line, sorry, probe high to probe low. So now you're measuring between those 2 points, which are those 2 red leads. Again, hardly any leakage current seen between those 2 points. So the designing of this product was designed properly to not leak any current coming out of this point, going back to the ground state of the product. All right, so that was the patient auxiliary leakage current, and then it gets us to the main focus of what an additional requirement is, the mains and applied part. Now this is a really complex test where it requires you to apply line voltage to your applied part. Again, your applied parts are these 2 things here. So you have this device under test, which is your medical device. You have this and this as an applied part that's going to be connected to a patient. So what I'm going to do is I'm going to connect that to an MD, but now I'm going to simulate an MD coming in contact with line voltage. So line voltage could come in contact with, could be, I'm sitting in a medical, in a hospital bed, a lamp falls on me while I'm connected to your EKG meter. So if a lamp falls on me, that lamp might kill me, but does that allow your medical equipment to send current or allow this current to flow, even causing me more harm? So this is kind of simulating what happens if one side of the measuring device, a human being, comes in contact with the line voltage, which is your MD, and is still connected to your device under test, which is your medical device. In order to do that, you need an isolated transformer, another isolation transformer, transformer T2, and it's going to also have a reverse polarity here. So it does reverse polarity to get the maximum amount of difference that you may see. The lamp could be on a different band circuit and is going on a different sine wave, while the medical equipment is running on a different sine wave. So we want to be able to simulate what happens if they're both on an opposite scale of the frequency. Do I create additional leakage to this MD when the patient comes in contact with line voltage? And the video for that is kind of just a little complex video, but I'm going to show you how. I'm going to pause it for a second. So we have a transformer T2. So we use an isolation transformer sold by our sister company, or APT Power Supply, that provides isolation transformer for all-in-one system, where we're going to take an output. So this is an output here from our isolation transformer. So this is T2 coming out of this APT power source. We're going to take that and plug it in directly to the to one of the applied parts. So again, I have to be able to switch this, and this is where I was saying, if you don't want to be dependent on operators to make all your switching, you could have a scanning matrix where it's doing the switching for you. So I'm taking line, neutral, and ground from my T2 source, and I'm going to be able to connect that to one of the applied part through my measuring device using these scanning matrices. So I could have this point connected to this point with the scanner in a correct mode, and then I could have these 2 shorted together to create this mains and applied part test that's required. Again, this could be said to be a fully automated test as long as you're using some of these scanning matrices to run your test. And we're going to, so this is the connection. Again, this is showing you how T2 is connected. Connected back to the our instrument that's going to measure, that has the MD in there, and the MD is connected to an applied part on a medical device. Okay, we're almost towards the end of our webinar. I know we ran a little bit over, and I do have a second poll question. I know we went through a lot of stuff about the leakage current testing, and it could be still a lot of material, and we're always here to kind of go over some of your setups that you may have. So this question is, how confident are you about the leakage current test that you're performing or currently being performed according to the standard? So I'll give you a few seconds to answer this poll question, and then we could wrap things up really quick. All right, the audio may have cut out. Can you hear me, Brittany? All right, sorry about that, guys. Just maybe I'm not getting the audio in from Brittany to kind of tell me the poll results. But I'll definitely take a look at the poll results. And if you guys have any questions, again, there's additional tests that may be required. They're like patient leakage current testing. We talked about mains and applied part testing, but there's other tests like external voltage on SIP-SOP. Again, what happens if somehow external signal input port comes in connection with a line voltage? What happens? Also, external voltages on metal accessible part, which is not protectively earthed. There's additional switches. There's a lot of switches, a lot of complicated setup that you may have. But we're able to achieve all those setups just using kind of breaking down the figure that they're referencing and how all these figures kind of correlate to how our instrument is doing the test. It may require additional equipment like the scanning matrices to kind of do this fully automated fashion, but there's no saying that this can manually. If you have enough time for somebody to go connect different points, it could be done manually, but that puts you in path of having not knowing if the test was performed properly or not. So using scanning matrices, it does allow you additional of performing the test fully automated fashion. If you have any questions, again, reach out to us at brittany.socha at airisafety.com. You can also visit our website, airisafety.com, that has white papers or additional contact information, our archive webinars that you could go through. Again, my name is Bishan. Feel free to reach out to me if you have any questions. I do wanted to point out that there is a webinar next month, which will probably be it is our last webinar of the year. We'll be talking about automating a production line. So 6 ways to fully automate an electrical safety testing station. So join us next month, November 15th, 10 a.m. Central Time. And unless there's any questions, I know we ran over on time, so do email us your questions, and we'll definitely get back to you. Thanks, everyone.